My name is Alex Blanda. I work as a software security engineer for Intel's Open Source Technology Center in Romania. Today's talk is focused on a fuzzing approach that targets system components in Android. The main points of the presentation. First, we'll have a section that deals with a set of general methods and concepts that can be used for fuzzing in an Android environment. This approach will not try to offer a complete picture, but rather to give an example or a starting point for someone who is interested in this topic. Then we'll see how this approach applies to several real-life fuzzing targets from the Android OS. We'll see how the approach applies to fuzzing Stagefright, which is the media framework in Android, and then we'll see how this approach applies to the Android application installer. Towards the end of the session, we'll also have an alternative approach. We'll discuss how to use the popular American fuzzy loop inside the Android OS. These will be the main topics for the general fuzzing approach. First, we will see a few methods in which we can generate the malformed data for our fuzzing needs. The actual execution or running of the tests won't be taken into consideration for this section because this is a process that is highly specific for each target. So we will discuss about this in more into detail for each example, for each project example. Then we will go on and see how we can monitor the results inside the fuzzing campaign in Android. We will see how to do this and to get the results in real time. In the fortunate case, when we are running a fuzzing campaign and we have a lot of results or a lot of crashes, we need a way to automatically sort out the unique issues. So we can develop a triage mechanism. We'll see how to do this. And in the end, when we have only the unique issues, the few unique issues, we need a way to analyze them, to debug them, to sort them based on their severity and to see if they're exploitable or not. So generally speaking, when we talk about fuzzing, we have mutational fuzzing on the one hand and generation fuzzing on the other hand. Mutational fuzzing means that we take an initial set of valid inputs or test cases and we try to apply different mutations to them. We need to take into consideration that while applying those mutations, we need to make sure that the target component, the system that we are fuzzing, needs to believe that the input that we are feeding is valid. So we need to fuzz those initial test cases, but keep them structurally valid. The approach on generation fuzzing is based on the fact that we try to create the malformed input from scratch. We need to know the internals of the format or the structure of the data that we are feeding to the target. And based on that format, we need to try to create an input that is also malformed but also structurally valid. For the projects that I'm going to talk about today, this is the toolset that we've been using. So first there is the basic fuzzing framework, which is a mutational fuzzer that targets applications that consume file input. This tool, the BFF, is based on another popular tool, Zuzuf. It's based on a modified version of this tool. Then we have Fuzzbox, which is actually a very small tool, but a more specialized one. It specializes in targeting multimedia codecs. Both of these tools work on Linux environments. Then we have Rodamza. Rodamza is actually a collection of many small fuzzing tools. Its main advantage, and the reason why we used it for our projects, is the fact that you can pass a seed to it, so when you actually get a crash, you can easily go back and reproduce that crash. And also there's the American fuzzy loop. I think you are all familiar with it. I'm going to talk more into detail about it in a separate section of the presentation. So let's say we've generated our data and we've executed it on the device. We need a way to see what happens, if it's possible in real time, with the input that we are feeding to the Android OS. If you are familiar with the logging system in Android, you know that you can access it through the logcat command. The thing is that each time a fatal crash occurs, so each time a crash occurs at the native code level in Android, a fatal message is generated and inserted into the logcat buffer. The logcat buffer contains messages sent from all the system components and not only from applications as well. And they are sorted using priorities. There are in total 7 priorities for messages that are included into logcat buffer. We are interested in the fatal messages. So what we do, each time we send a test case to be executed on an Android device, we also artificially insert fatal message in the logcat buffer. So for example, this is an artificially inserted message into the logcat buffer. You can see it has a fatal priority here. You can mention using this command the priority, the component, and other useful information about the test case. Usually, I'd recommend that you insert here information about how to actually reproduce the crash. For example, if you are fuzzing media files, this would be a more simpler example. We could include here the name of the media file that was sent to be decoded on the device, and then have that media file saved, let's say locally, on the local machine that is connected to the Android device. So each time we send a test case, we log it, and when an actual fatal message that is actually generated by the system, like this one, let's say a segmentation fault, we will have a way to reproduce that crash. Because the test cases are sent sequentially, we know that this segmentation fault is produced by this component. Also, as I said earlier, it's important to note that we must include in the message a way to actually reproduce that crash. Because in some cases, it won't be possible to actually save the input that caused that crash. You can have information like a seed or stuff like that. So we've generated the data, we've executed the data, and we've generated the logs for a testing campaign. Let's say we've run a testing campaign for, I don't know, a period of time, 1 day, and we've generated that log that has the template that I mentioned in the previous slide. If we have a large number of crashes, and we can go manually through them, we can go and check each fatal signal and see the input that caused it and see if it's unique or not, and gather information about that crash. We need a way to sort them in an automated manner. What we do is, besides the fatal message that is generated each time a crash occurs in the Android logcat, we have an entry that is generated in the data tombstones files on the device. So we have a tombstone that is generated for each crash in Android. The tombstone file contains a lot of useful information. It contains the type of signal, the code for that signal, the value of the registries at the time of the crash, and the backtrace for that crash. What is interesting for us from the perspective of the triage mechanism is the program counter value for the last component in the backtrace, so this component. This value will be unique for each crash. The thing is that we need to carefully apply this mechanism, because if we are testing on different images, on different builds of Android, if we will have the same identical crash, the program counter will differ. So this mechanism applies only if we are testing on the exact same build, on different runs. Here are more details about the actual implementation of the triage mechanism. So let's say we had the initial testing phase where we executed the files and we generated the logs that have that specific format. We save the logs with that specific format and we parse them, identify the crashes, see what input produced the crash. It can either be directly the file that produced that crash or ways to reproduce it. And for each of the identified inputs, what we do is try to confirm the crash. We resend it to the device, see if it actually crashes the device. If it does, it must generate a tombstone. So we grab that tombstone, we check the program counter from the backtrace, and if it's a value that has not been previously encountered, then it means that it is a new issue. What we do then is we save the tombstone because we want information about that crash, and also we save the input if it's possible, or the exact information about how to reproduce the crash. After sorting the unique issues, we are left with a number of, generally speaking, in most cases we are left with a number that we can go through manually and try to analyze them. The first place we go to see information about the crash is, as mentioned earlier, the tombstone file. The signal type and the signal code can give us the first clues of what's going on with that crash. There are also useful information in the registry values. The tombstone file generally contains useful information from Locat, so additional information besides the stuff that is on the screen. Where else can we go? We can go to the message. Those are two examples of crashes on Stagefright. The first is an error 4 and an error 6, and this is how we can identify what is going on with these errors. So one is an invalid read and one is an invalid write. Generally speaking, in Stagefright, these are the types of issues that we've encountered, but I'll talk about this a bit later on. You can also use GDB. For that, you first need to enable GDB server on the device. You can do this in two ways. You can either start the process that you want to debug and then attach the GDB server to the process ID of the target. Or you can actually, if the process can be started using an executable or a binary, you can start it directly using GDB server and mention the port that will later be used from the local machine to mention the target. Then all you have to do is forward the TCP port on the local machine, on the machine that is connected to the Android device. Start GDB, target the remote port, and resume the process execution. It's also useful if you have the Android tree and you've built an image that you've actually flashed on the device. You can load the debugging symbols and have more information on your debugging session. If you have access to the source code, which is the case of Android generally speaking, there are some binaries that you don't have access to the source code. You would like to know what was the exact line of the source code that produced the crash. For that, you take the tombstone file and the backtrace, and you identify the program counter value for the component that you are debugging. In the example on the screen, we don't really want to see the exact line of code from the functions from libc, but actually we want to see the component that crashed in libstagefright, for example. And that is why we take this program counter value and pass it to address to line. This is the path to the symbols from the Android tree. So you need to build an image and actually flash it on the device in order to use address to line in this way. Okay, and now I'm going to move on to the first example, how we applied the things I've mentioned until now onto a real testing scenario. The Stagefright framework is the media framework in Android. It has been highly publicized lately because of the so-called Stagefright bug. I'm going to try to show you how to actually perform fuzzing against it. First of all, a few reasons that make audio and video attractive vectors, attack vectors. First, there's the fact that audio and video are binary streams that contain complex data. So these streams are parsed by a lot of specialized components, which can result in a lot of memory issues, memory corruption issues. Then there is the fact that we have a large attack surface. This means that the chances of finding an issue that is actually exploitable are a bit higher. In Android and in general, I think, there is also the user perception that media files are harmless. So normal users won't have any second thoughts when downloading or playing media files from untrusted sources. And also in Android specifically, because it has permission-based security model, you don't really need any special permissions when, for example, surfing the web and downloading a media file and playing it. Or also there was the attack vector that made the Stagefright bug popular, sending the media file through an MMS. This is the overview of the testing process in this case. So what we need to have is an initial large set of valid media files. We try to fuzz them, so to malform them in various ways using the toolset that I mentioned in the beginning of the presentation, but in the same time trying to keep them structurally valid. We then direct them to the appropriate decoders. So for this specific case, the target is the Stagefright media framework. We monitor the system for potential issues using a very similar approach to the one that I've mentioned earlier. And then, because it is the case, the project gave a lot of crashes, a lot of results, we passed the results through a triage mechanism and analyzed the issues separately. In the initial stages of the project, so this project began sometimes in March 2014, we looked and tried to figure out how to actually pass the invalid media files to our target. The first solutions were passing the media files to different player applications from Android, or trying to use the Java API. However, the best solution we came up with was the Stagefright command line interface that can be optionally built from the Android tree into and then pushed onto an Android device. This had the main advantage that it bypassed the Java layer, so we had access directly to the native code layer of the Stagefright media framework, and that is actually where all the crashes occur, all the issues appear. This is an example of the usage of this binary. It has the main functionality of decoding audio and video files. Also, for audio files, it can offer playback capabilities. There is the advantage also that you can try to force the usage of a software codec and a hardware codec. So we had to test in both scenarios. And there also is the possibility of extracting the thumbnail for the video file. This is also a place where crashes can occur when parsing the image associated with the video file. This is an example of an actual log that is constructed using the approach I've mentioned earlier. For this specific example, the files were malformed using the basic fuzzing framework, which, as I said, is based on a modified version of Zuzuf. So each time what we do is we have the initial valid media files, we fuzz them locally, so not on the device, given performance issues. And then for each fuzzed file, we send it to the device, we push it onto the device, and try to decode it, passing it as a parameter to the Stagefright binary. Each time we do this, we also insert the fatal message with the file name. So in this case, this is simple. We have the file name of the media file that is also saved locally on our computer. When an actual segmentation fault appears, we will know that this file is responsible for this crash. And it will be easy to reproduce it because we have the file saved. These are some results. So the project, as I said earlier, began in March 2014. This was the time when we first reported the first issues to Google. The initial results, so during the first week on a cluster of devices that was composed of less than 20 Android devices, we had thousands and thousands of crashes, and that's why we had to come out with automated triage mechanism to sort out through the unique issues. The first severe issues that affected the Stagefright library were included in the Android Partner Security Bulletin from September 2014. These were integer overflows, much similar to the issues that are commonly known as the Stagefright bug. They have the CV IDs from the screen. The tool is now open sourced. It has been open sourced in February 2015. It's available on GitHub. We don't actually use it anymore as it is. We use it as a complementary solution alongside with AFL. I'll be talking about this towards the end of the session. I'm going to move on towards the next project example, which is fuzzing the Android application install process. This is an interesting project from a few perspectives. First, there is the fact that the component that handles the install process in Android, more specifically the install daemon, runs with high system privileges. So any issue that is found and is found to be exploitable can be considered to be a high profile issue. Then having an APK, so an APK is the file that we use to install an application on the device. An APK is the file that contains the compiled Java code and the native libraries. It's one of the few ways in which an unprivileged user can send input towards system components, towards privileged components in Android. And also there is the fact that issues that are regularly found by fuzzing are not usually found by regular validation, so are not found by checks that are done, for example, before the applications are uploaded into the Play Store. We've identified two testing approaches. One is specific to Android versions before Lollipop because of the Dalvik art switch. So before Android Lollipop, we had the Dalvik virtual machine. After that, for Lollipop and Marshmallow, we have the Android runtime art. While documenting the steps that are taken during the regular install process in Android, we've seen that there are two components for each of the Android versions that are interesting from a fuzzing perspective. In the case of Lollipop and Art, it was this component, Dex and in the case of KitKat and other previous versions and Dalvik, it was this component. Dex takes a Dex file as a parameter and converts it to an OAT file, which is actually a regular ELF executable that is then used to open the application. The file is stored on the device and it's used to play the application. Dexop uses a different file format, so it converts the Dex file into an optimized Dex, which is then stored onto the device. So these are our main targets, the Dex2out and the Dexop. The thing is that the installed daemon, which is the component that runs with high system privileges, forks these processes without dropping privileges, so these are in turn privileged components. This would be the general testing flow. We need to have an initial set of valid APK files. From these valid APK files, what we do is we take each APK and we extract its components. This is basically an unzip operation because the APK is generally speaking just an archive file. Then we fuzz the APK components that are of interest to us. And then in the case of Dalvik, we need to repackage the APK and send it to the Android install process. In the case of Art, the things are more simpler. We can actually pass different components directly to Dex We'll see about that. These are the components of an APK. The things that are of interest to us are the classes.dex, because this is the file that we will actually be fuzzing. An alternative fuzzing target could be the Android manifest XML, but this is not in the scope of this project. Metainf directory contains the signing information for the APK. So, for example, if we have an APK, we unzip it and we start to modify things around it, the manifest file or the Dex file, and then we repackage it and try to reinstall it on the device. That won't be possible because the signing information won't match. So after we modify anything in the APK component, if we want to reinstall that application, we need to resign it. This is the approach on Android KitKat on DexOpt. The thing is that although DexOpt is a standalone binary in the Android device, so you can see it in the Android device, you can pass, there are a lot of parameters to pass to it, and these can be obtained from a shell-like environment. So what the solution that we came up with was to actually simulate the entire APK install process. And for that, so we take an APK, we unzip it, we fuzz the extracted Dex file. For the moment, let's say we fuzz it, and I'll explain later exactly how we do this because it's important. We remove the original Dex from the initial APK using the AAPT tool. We repackage the APK with the new fuzzed Dex. This is done also with the AAPT. We need to create a key store so we can actually sign that APK. We do that with the key tool. We remove the old, outdated metainf directory, and then we resign the APK. Then all we have to do is just run adb install and try to install that APK. DexOpt will actually be responsible for parsing the corrupt Dex file, and any issues that will occur generally occur into this component, into DexOpt. This is an example of a log that is constructed using the fuzzing approach I've mentioned earlier. For this scenario, we've used the Rodamsa tool. So what we need to have in each message that is inserted into the lookup buffer is the name of the APK, the name of the initial valid APK, and the seed that we have used to fuzz the Dex file. Now, we don't actually save each malformed APK, we just have the initial APK saved in one place, and when we encounter a fatal signal like this one, a segmentation fault, all we have to do is take the initial valid APK and pass it through the process I mentioned in the previous two slides. And at the fuzzing step, we can use Rodamsa to fuzz the Dex file with this seed. And this should give us the exact APK that produced the crash. In the case of Dex2out, the things are really more simpler because also Dex2out is a standalone binary in the Android device shell. You can pass a Dex file to it and an OAT file that is the output. So all you have to do is just run Dex2out -- Dex file and the Dex file you want to pass it, and -- out file and a file name for the output. This is the log example for this case. We have the name, directly the name of the Dex, because in the case of the Dex file, we don't really need the APKs. So what we do is we have the initial pool of APK files, and we extract from it the initial Dex files. However, if we do encounter a fatal signal like this one, we take the initial Dex ID and fuzz it with Redamsa and the seed. If Dex2out crashes, so we have a crash in Dex2out, we actually also try to reproduce the crash in a normal user scenario. We try to include the Dex file into the original APK and try to produce the crash using this scenario also. So, for example, if we would want to include a POC in a report, we would include the Dex file, but also the APK file that would produce the crash. It would be the same crash, but with two different attack vectors, let's say. As I said earlier, the actual fuzzing of the Dex file is a little bit tricky. We've identified 3 ways of performing the fuzzing against the Dex files. The thing is that the Android OS employs a large number of verifications at install time against the Dex file to check if it's actually valid. So we've identified these 3 alternatives. I'm going to go through each one of them. The first one is, so these are examples of install verification errors. So if we have an initial Dex file, and we start modifying things through it, these are the types of errors that we would encounter. For example, bad file size, bad checksum, invalid header. The thing is, we don't want these errors to appear, because it means that the system didn't actually parse our input. It just stopped at the header. It saw that the things aren't all right, and there isn't a way actually to produce a crash in this scenario. So what we want to do is to trick the system into believing that the Dex file is actually valid. For this, we need to understand the Dex file format. I'm not going to go very much into detail. There are a few important sections. First, there is the header that contains general information about the file, things like header size, file size, checksums, magic numbers, endian tag, but also specific information about each section. So for each section, for the type IDs, proto IDs, the header will contain 2 fields, the offset for that section and the size for that section. The fields contain the actual content from the compiled Java code, from the compiled Java code, and also there is an optional field, the map, that contains information regarding the offsets and the type of content that is inside each section. So the first alternative would be take the Dex file, start fuzzing randomly the file, and then come back and try to repair as much as possible. In this case, what we can repair is the magic number, which is a constant, the checksum, because we can recalculate the checksum for the resulting file after the fuzzing has been done. This is also the case of the SHA-1 signature and the file size. These can both be recomputed. The header size and the endian tag are constant values, and if by any chance we modified it during the random fuzzing process, we come back and we insert the correct values. The second approach is a more targeted one. Because the data section contains the most interesting information like strings and variables, we only fuzz this section. So what we do, we take the initial Dex file, we split it in 3. We have the first part with the header and all the sections. We had the second part, the data, and we have the third part, the map. We fuzz only the data randomly using Redamsa, and then we glue all the chunks back together, and we come back to the header and try to fix as much as possible. Besides the fields from the header that we've fixed as in the previous approach, we can also take a look at the map offset. So for example, if we If we fuzz the data and it grew in size, the offset of the map will change, and this field can be computed. We have information. We can actually calculate how big is the fuzz data file, and also the data size. This is actually the approach that gave the most promising results, so the most crashes and the most interesting ones. There is also this approach, which is a completely dumb fuzzing method. We just take initial valid Dex files and we pass them through the basic fuzzing framework. We don't look at the header at all and just pass it back to the Dex binary. This would be an example of a log in this case. For this scenario, we save all the invalid Dex files that are being generated, and if an actual segmentation fault occurs or other fatal signal, we will have that Dex file saved on the local machine. These are some results. So the number of crashes wasn't as spectacular as in the case of Stagefright, but in the initial phases of the project, we had about 1,000 crashes not unique per week on a cluster of 30 to 40 Android devices. There is a critical issue that occurred using the targeted fuzzing approach. We've reported it to Google, and it got a CVE assigned in 2014, in November 2014. There are also a lot of low priority issues that were reported both in KitKat and Lollipop, but these were not considered to be exploitable. The project is still under development, so we have a lot of issues that are under investigation. I'm going to speak a little bit about an alternative approach that uses the very popular American Fuzzy Loop tool. A few words about the tool in general. It's an instrumentation-based fuzzing tool. It offers two fuzzing modes, the dumb mode and the instrumented mode. It also has a third, let's say, mode, the Peruvian rabbit mode, that you can feed crashes to try to get new crashes from crashes that already occurred. Its main advantage is the fact that it detects changes to the program control flow, and it can find new paths and find new interesting test cases that can be sent to the target. It's pretty much automated. It detects both crashes and hangs. It tries to do a best effort to sort out the unique issues. I used a modified version of the tool, a version that was developed by my colleague Adrian. He developed a port for the tool for Android. It's publicly available now. It's on the mailing list from the AFL tool. This is how we used AFL to fuzz Stagefright. If you've ever worked with AFL, you know that there are a few prerequisites before actually starting the tool. In the case of Android, what we need to have on the device is have root, remount the device. The root and the remount are necessary so we can push the AFL testing binary and also the target binary. For example, in the case of Stagefright, because the binary doesn't come built into the default Android tree, we need to build our own binary and then push it on the device. If we want to push it on in system bin, you need to have the device remounted. Also, you want to load the initial seeds, the initial valid media files, and a prerequisite that is specific to AFL is to set the scaling governor to performance. The thing is, if the initial media files contain an input that generates a crash from the beginning, the AFL tool will reject it. So if you want to automate this, we need to make sure that the initial seeds that we load onto the devices do not contain inputs that produce a crash. When we are working with a cluster of, let's say, tens of devices, we need to figure a way to do this in an automated manner. So what we tried was we start the AFL tool with a timeout and check if it finds a crash that input that produces a crash, and if it does, wait until the timeout ends and restart it again. So we have a loop with AFL running with a timeout. When it gets rid of all the test cases that produced a crash, we will then go and start AFL normally and redirect its pretty results reporting format to dev null, let's say, so we can run it in an automated manner. This is a diagram that shows how we've integrated our custom fuzzing tool with AFL. So we have the initial phase, the seed generation, where we generate initial valid files, media files. We load the seeds onto the devices, where we start AFL using the process that I've mentioned in the previous slide. We run the AFL tool for a period of time, usually 2 or 3 days. Then we get the crashes and the hangs. The thing is that on each device, AFL will report an issue as being unique, but another device will also report an issue as being unique, although the issues aren't unique for the general target. That is why we need to pass the crashes, the results that AFL gave us through our custom-based fuzzer. We pass it and we generate the logs in the format that I've mentioned earlier, and from there we have the logs that are parsed and passed to the triage mechanism, where we actually get the real unique issues. There is also another reason why we need to pass the media files through our custom fuzzer, is the fact that the media files run in a restricted environment in AFL. So you can, in Android, for example, you have to set the memory limit and the timeout, where in the case of our fuzzer, the media files run more closely to a normal user scenario. So some crashes that are reported to AFL may not actually reproduce in a normal user scenario. We've also had some results using this approach. The most notable was a heap corruption that could lead to arbitrary code execution using the mediaserver process. This was discovered this summer. It was included in the Nexus Security Bulletin from August 2015. There were also a lot of low priority issues, things like null pointed references or integrity division by zero stuff. And that's about it. A few conclusions. First of all, fuzzing in an Android environment is a little bit trickier than in a normal Linux environment. Also, Stagefright is not really a bug. It's more like a library that has a lot of issues. And it's really important to know the internals of the component that you are targeting, so you can actually have better results. There is also the case when you perform down fuzzing and you get lucky. That's also a probability. And that's about it. These are other people that contributed to these projects. Adrian developed the Android port for AFL. Costel Maxim also had a lot of technical input for the projects. Ionuț Gavaz supported the development of these projects. And also, if you have questions.